Everyone, good afternoon, good evening, wherever you're joining from. And welcome to another conversation in Future World Conversations initiated by Future World Alliance. Today, we are exploring a topic that is becoming more important as AI moves from experimentation into real world systems. That is, how do we build AI that is scalable, trustworthy, secure, and resilient? AI is not part of business operations. AI is now part of business operations, education, healthcare, finance, and everyday digital experience. But as organizations adopt AI at scale, the challenge is no longer just building models or using tools. It is about creating systems that people can trust, that can handle complexity, and that are designed with governance, reliability, and responsibility from the beginning. We are excited to have Hemasundar Reddy Lanka here leading today's session here. Hemasundar is a technical architect and AI data engineering leader with over 20 years of experience across enterprise systems, cloud native architecture, distributed systems, real time data engineering, and digital transformation. His work spans from financial services to healthcare to technology with a strong focus on data ecosystems, trusted data ecosystems, scalable AI platforms, intelligent automations, and resilient enterprise architecture. So today he will be sharing practical insights on building AI systems that are not just intelligent, but also dependent and ready for real world impact. With that, without further ado, Hemasudhar, over to you. Thank you so much for leading this session for Future World Alliance.
Thank you for Padma for intro. She already explained about my bio. Thanks to everyone joining today. So let's get into the presentation. So today I'm going to explain about or discuss about building a resilient AI system in distributed environment. Why we need this one and what are the challenges on AI ecosystem and how we are going to achieve. This is kind of a some real-time experience from my past 2 years. Whatever we are migrating from. Um, uh, Migrating from previous before AI and post AI, how the things are going on, how we are handling the data, how we are trusting the systems, building the trusted layers, all those. So let's get into the details. Okay, we are going to discuss about these layers, these 7 layers, why resilience matters, distributed AI architecture, consistency and saga patterns, how we are going to use in distributed environment, hallucination and drift resilience, observability for AI, enterprise lessons learned and the agentic AI feature. So, okay, why resilience matter? So nowadays, AI is no more practical. It's not kind of just kind of a chatbot. It's a kind of every organization is building the agents and creating the pipelines and implementing the processes, more relying on the AI. If AI fails, things will be different than before AI fails, how things will be. Before AI fails, we know what are the failures and system, we can easily identify there is a failure. But in AI failure, it's a different. It will confidently give the answer even if there is a failure. We'll see infrastructure is fine, environment is fine, systems are running fine. But if there is any data disturbancy, AI level, any LLMs having the issues, but it's very hard to identify and it will give the confident answers with the wrong information. So that is very challenging part to identify then before AI systems. So that is when any organization going to use the AI, they need to consider all these aspects, how they want to handle and how they can design their systems. So here are the different things how traditional system failures handles and AI specific failure models will handle. If there is any crashes happened, timeouts happened, system will throw those exceptions, or we can have alerts or monitoring systems. They can easily identify and a kind of a same failure will give a same result. For example, when we are ordering something, if order system is down, always will get the same failure instead of giving the different reasons. And root cause of that traceability, single component, if order system is down, if order, that response is not getting properly, if you are getting 500 or any 404 or any kind of errors, we know which system is failing by monitors and everything. We can go and we can focus on that specific system and we can fix it. And it's a well understanding, monitoring, and alerting system. Once you set up the monitoring based on these failures, we no need to go day by day, adjust that failure, what kind of failures we are going to get. But in AI specific failures, it's hallucinations, confidently give the wrong answers, no deterministic. Same input may get a different versions of output if the data is not consistent, context is not proper, or any looks like it's disconnected again. Let me share it again. Okay, and cascading failures across the chain of models. When we are building the agentic AI system, there will be multiple models will be interacted one service with another services. If one model is failing, it's very hard to find out which model is failing, which model is giving the wrong information. So to overcome this one, to monitoring this, to identify the things. So we need to build the proper system when we are migrating to AI, uh, uh, AI specific services. What do you mean by AI resilience? So reliability, the system keep functioning correctly under a load, particular failure, and an unexpected input. Whatever the case, system should behave exactly the same how the way we designed. Trustworthy. The outputs, expected behavior shouldn't be changed, and always how the way the specific functionality or task needs to be completed. It should work that trustworthy. And security, resistant to prompt injection, data poisoning, and unauthorized access to models or data. Like here, mostly AI systems will work based on the prompting. If system is not secured, this data can be poisoned through the uh, prompts or whatever the way, then traditional systems. So that needs to be handled securely, and uh, the specific system models or data layers should be under the specific secure controls. Observable drift, cost, latency, accuracy, and visibility in real time, not discoverable after the fact. Like the specific failure or cost of the system and visibility of the real time. For example, basically everyone knows, right, how the prompting and the AI will works. It's based on the tokens, and based on the tokens, cost will be vary depends on the situation, and sometimes based on the systems. For example. If it is a retail system, usually in the holiday season and offer season, like Thanksgiving Day, those times, the load will be vary and cost will change if you are using the AI systems during the time. The entire things and structure will be changed during the time. So we need to identify those facts before going to the situation instead of once we get into the problems. And adaptability. The architecture absorbs model updates, new data sources, and changes business rules without redesigning. We build a system using the AI. AI is the like nowadays we are going with the microservices, distributed systems, and easily migrating the systems by simple. We can deploy our artifacts anywhere, anytime. Today we are deploying on-premises system. Tomorrow we are going with a cloud system, whatever. And data sources today it might be in RDBMS. Tomorrow it might be big data, or it may be somewhere else. When we are adopting these things, this AI based systems should adapt easily without redesigning the entire system. So these are the considerations with AI resilience we need to consider. Okay, AI resilience framework, 4 pillars. Architecture. Architecture is like how we are going to architect. So instead of building a big system, a monolithic system, it should be a distributed, decoupled, fault isolated services, kind of a microservices, simple events, and saga patterns. I will go and in further sessions, slides, I will explain what is the saga and what kind of patterns we are going to uh, cover during part of a saga. Okay, model integrity. hallucination grounding, drift detection, multimodal fallback strategies. So basically in this pillar, what we can hallucination groundwork, what we discussed. So if something goes wrong, uh, AI system will confidently give the wrong answers and drift detection. So these answers we need these the kind of a wrong failure scenarios we need to detect uh, as I mean when we are designing the system multimodal fallback. So if one system is failed, how other system can provide the same services. These are kind of a circuit breakers, fallback strategies we need to consider, and human oversight. Humans should be in loop, checkpoints in some of the risk and decision impact. Kind of a, for example, when someone is applying for a loan, we'll check the credit check first, then next whether he's eligible or not. At final step, instead of completely depending on that system, there should be a human check. Is this the trustworthy? Is this the accurate validation? All those things. So yeah, some places human oversight definitely required. Observability, end-to-end tracing of accuracy, cost, latency, and drift accuracy in every services. In distributed service, each component has a each process has a individual service. It's running on its own and different environments and connecting through either uh, streaming or some services, whatever. So end-to-end tracing is the one of the challenge. So that needs to be taken care. And cost, latency, between the services, any drift across the services. Like if we need to easily identify where the specific task is failing and what is the data drift happen. So that needs to be identified. Distributed AI architecture. Out of that four pillars, we are going with the distributed AI architecture, microservices. In distributed architecture, we are going to cover microservices, event streaming, and enterprise reference patterns. So autonomy of modern AI system, something like this. Users can call applications, applications will call AI services will call data and knowledge systems. Those can be vector stores or data warehouse or knowledge graphs. It can be database or whatever, and inferences. So out of this, failure can happen any stage. We need to identify it can be happen during the user request at the application layer, yeah, or AI services, or maybe data layer, maybe infrastructure as well. So we should have a guardrails at each layer level, what kind of failures we can identify those potential failures. We need to put the specific monitoring tools and whatever. Okay, AI is a distributed system. So AI is not a single component, or it's not getting from one. It can be multiple models, or it's different systems, different LLMs using the different agents. So multiple services, multiple models, multiple data sources, multiple patterns. When we are designing, we need to consider these things, how we can integrate all these when we are building entire system. So architecture-wise, we have basically this is a like a traditional architecture. It's a kind of similar architecture we'll follow using AI as well, but sorry about this one. I think it's continuously disconnecting my screen share. Okay, API gateway identity. This is the layer basically when any request is coming to the system, it will identify whether that specific request is authorized and the specific request is having a authentication. Or, for example, one when one system is trying to access connecting to any external systems. So they should have some security principles. They should be established before going to that one. So all these security wise and authorization, everything needs to taken care in API gateway layer, and which system needs to go to the specific request once it's authorized. Everything those kind of load balancing, everything will be handled at a API gateway layer and microservice layer. These are the independent services doing their task independently. Once the task is done, then the service process is going to complete. when we are going with the microservices, connecting different services, either it's a event streaming or using the REST endpoints or messaging system or some flat files, and it can happen anything through the communication. But most of the cases in AI architecture, going with the event-based architecture, so that that specific service can focus on only that specific task. Once the task is completed, that response can post to the event streaming. Then it's no need to worry about the next steps. Next service will come into picture and will take that subsequent. For example, when order processing is going on, first fulfillment service will do the job, and once fulfillment is completed, next service is payment service. That payment service, okay, my event is in event streaming, that will pull and that will process. And on top of that, AI services will be there. Those are LLMs, RAG, ML models. So those, if there are any agents built in even AI services, those easily can plug into the system, and they can pull the messages and they can process their job. The specific model do the job, and it will respond back and pull the message back to the event processing. And data layer also, it can be independent. So this data layer, again, as we discussed, it can be anything like a vector database. It can be a traditional database, or whatever, where that specific data resides, and trying to pull the data from there. And any service can connect through the event processing or whatever the way building the system. So it can easily pull that. I mean, communicating the service to service. And observability and governance. That is a major thing we need to consider. Um, when this is kind of a system, dis services are distributing different things, how process is going on and how the task is going on, where the task is, what is the process status, everything. That we need to have some global observation to find out how the process is going, to find out the failure scenarios, and to reprocess if there is any task stuck in one of the status. So that is a major challenging observability and governance. Okay, what are the benefits of a microservice for AI? We can independently deploy per model or services. It means some of the services can be go to the cloud, or uh, we can get as a uh, I mean external services instead of building that services, software as a services. Those things we can easily plug into our system, and horizontal scalability under variable load. So when we build the system, microservices, some services require a more load, some services may not be required uh, much attention. So in that case, the specific services, whatever we need, more instances, we can easily scale that uh, horizontally whenever it's needed on demand, instead of a entire system is like a, if it is monolithic, basically we need to, for example, if load is more, we need to increase the size of the systems, increase the scalability for entire system. In this case, by using the microservices, we can scale only the specific service which is required, what is the services taking the more load. And fault isolation. One model fails doesn't take down the entire application. So if one of the service is failing, for example, when we hitting when a system trying to hit order processing system, trying to check the item catalog. If item catalog is down from one of the sources, entire system no need to be go down. We can have a fallback mechanism, circuit breaker, or we can have some down like a later processing systems, like as we are using the event-based architecture, this request will go and sit into the streamings, that is a Kafka, or wherever. Once the system is ready, that will be processed and it will respond back with the details. So it's easy to handle, and teams can iterate on the models without full redeployment. It means we have multiple services, multiple systems. We want to upgrade one of the system, one of the model, without impacting entire system, entire deployment. We can focus on specific system, and we can do the upgrades on that system. What we need what we need to manage in microservices. Network latency between the systems, as it's not single transaction and data and services processes not sitting in single system. There will be a latency, like a connections, either it's REST APIs or it's a streaming or with Kafka events or whatever. There will be latency between the between the services when some task process is going on. Distributed tracking become mandatory, not optional. So when specific task is in process, it will go as an event between the services. Tracking is the challenging part where the specific task is, and that is a mandatory to build the system how we can track that, and monitoring and tracing that specific task. Versioning multiple models and prompts simultaneously. So when one system is upgrading with some contracts or some upgrading their models or technologies, anything, and in that specific distributed systems, other systems should align with that contracts and should align with sometimes the specific scenarios. What are the models depending on that one that needs to be updated as well. Data consistency. This is the challenging part. If one task process, for example, if task needs to be processed from multiple layers, uh, out of that, if certain steps got completed and it got failed at some certain step. So find out where that is one and how to revert back the transactions. That is a challenging part, and we need to implement some patterns. I'm going to explain about the Saga patterns, how we can do that one. It's kind of different systems. One system already completed, processed the task, and it's created the event, my task is completed. Second one also processed, completed the task. Third one failed out there. So that failure task needs to be informed. Okay, this specific task got failed at this stage. So it will come back to second service, that needs to be rolled back, and it needs to come back first service. Again, it will roll back. During this rollback, if second system is fails again to roll back, how we need to handle. So that's where we need to identify all the failure cases. First, we need to build the failure system, how to handle the failure cases. Okay, how the event-driven architecture, AI architecture should be like. So event producer, this is the one usually takes the prompt or request. Then this producer will put the request on the specific event into a Kafka's event streaming, that can become Kafka or whatever. So AI consumers will be there. Those are continuously listening that events from streams. I'm not able to pull this out. Okay. So AI consumer services will continuously listening that streamings, and it will if there is any event specific to that AI service, consumer service, it will read that message from topic. Then it will it will process to next state, and that next state will take an action that can be business layers. It will do the process, and then it will process to the next downstream systems to take an action. Exactly what is the prompt requested? We'll go to the event pass. From there, listeners will listen what is the request coming to the event through the event. Then the service will send that specific event to the state store. That kind of a data way, again, as we discussed, this is the specific information stored either in database system or data lake or whatever it is. So it will process that specific request, identifying that, and then it will send to the next layer downstream system to take an action. Okay, how the real-time events flow will be. Here, event is like just a small kind of a process or request. That event features like how it needs to be processed, and what are the layers models needs to be used to process that specific event. Then it will move to the inference. So in this layer, it will determine exactly the truth check, and there are any specific filterings and processes needs to be applied, then that will go to the decisions. Decision will be okay, what kind of event that specific task needs to be completed, and where which process needs to be processed this one. So the decisions will be processed, then finally it will go to the actions. So action is like either it can be respond back to the result, or it needs to be completed some of the activities, whatever. So event flow is like this. And when this in this distributed system, when these events are processing through the layers, through the streamings, multiple steps, workflows in this. So how we can handle the data consistency? Previously, as I pointed, if task is failing in middle, how we can do the rollback, and how we can handle, how we can identify whether it's a system failure or a data failure or whatever. So we can go with the different patterns. Like here, I'm going to explain about Saga pattern, how it is. In distributed systems, consistency is the challenging part. No single transaction, it's an independent transaction throughout the different systems, different microservices, and partially completion risks. And AI adds non-determination. Model calls pathways through workflows, can produce a different results on retries. Each retry, it can give a different result instead of a specific result when we are using the AI build services. And rollback logic. Business process coordination. Multiple services needs to agree on outcome, approve, deny, or escalate without a central lock. Okay, this is one of the example. We'll go through that one. Reserving the credit. To reserve the credit, receive the request, release the credit, and score fraud risk. Clear that flag that way as well, and generate the offer, discard the draft, and confirm the approval. Reserve the approval. So this process, this task can fail any stage. For example, it's reserve the credit, then when it goes to the fraud risk, if there is any fraud happen over there, it shouldn't clear that one. It should identify, it should be notified back how this needs to be reverted back. Sorry about this, it's continuously disconnecting. So in this case, if there is any failure happened, either generating a offer or confirming approval or a score fraud risk, credit are already reserved. So the system needs to be informed, okay, this specific task, this specific request failed at the specific stage. This needs to be reverted. So the specific system, when it's failed to confirm the approval, it needs, instead of confirming the approval event, it needs to raise it's a failed to confirm the approval event. That will go to the event streaming, and reserve credit service listens to the continuously listening the events. When there is an event failure event, it needs to listen back and needs to revert that process. I mean that a specific reserved credit needs to be reverted or roll back. Okay, in Saga, basically, there are two patterns. One is choreography, another one is orchestrator. Yeah, this is the choreography Saga pattern, service coordination via events, how the choreography will work. So, in the same example, we have four services. Four services are interacting through events. That is by using the event streaming, either Kafka or whatever. So, once that service, for example, in this case, credit service, once credit is approved, fulfilled, it will create the event or message saying that for that specific request, credit is approved. Then event will go to Kafka event stream. From there, once that message is pushed into that specific topic, fraud service continuously listening that topic. It will listen that specific event, and it will process the fraud services. If this fails, then it will create an event failure event. It will send back to the Kafka. Then credit service will listen that one to roll back. If that's successfully completed that fraud service, then it will create a successful message to the topic. Then AI offer service will continuously listens that one. If there is any message related to that one, it will read that and it will process. Then once it's completed, it will push back the success message. Notification service also continuously monitoring that events. Once that message comes, it will read the process and it will send the specific notifications. So in this ecosystem, this service is not depending on the other services what those are processing. It's independently doing their job, and it's pushing the messages or reading the messages to Kafka. Today, fraud service is something using a third-party services. Later point of time, this needs to be replaced. This can be easily replaced without impacting any other systems. But this needs to be integrated with that specific Kafka stream or event stream, whatever in the ecosystem. Now, for example, fraud service might be using traditional system before once organization decided they want to go with some specific service, they are depending on the AI or agent something, they can easily plug in here, but without impacting my system. But thing is that when these transactions or processing is going on, tracing of that specific event or data consistency is the challenging part. These are independent services. When something going wrong with the system, today this is using traditional system, tomorrow this can be different systems. So that tracing is the hardest part in choreography pattern. But again, it's independent services. They can upgrade anytime with any dependencies or whatever based on the specific needs. This is the choreography. Choreography is some advantages, something like we don't have a uh, specific common service to handling everything. It can be independent. It can handle anything, and we no need to do a master orchestrator to handle the events to trace those events. But again, disadvantage is tracing the events explicitly and monitoring the things. Building the monitoring system is a bit challenging. Saga pattern. This is a bit different. There is a master orchestrator that knows what events should go to which service. So this will handle the initial request, and this will send, okay, this specific event needs to go to that specific service, but it will be tagged. Messages still push to services, either through events or whatever, streamings or whatever. But master orchestrator has the control, and to monitor the events, it's easy, where the failure and where the process struck, if there are any issues. So most preferably, this is the one can control easily. But again, when there is any system upgrade happened, master controls should know what kind of system upgrade is happening, how they are communicating, and whenever change happen here, and master also some changes are required to taken care. Hallucination and drift resilience. Model specific failures, model and how to design around them. So as we discussed, AI system, when AI system fails, it's very hard to find out the failure. Always will get the confident answers, but at the same time, that it will give the wrong answers. That needs to be identified. So to overcome this issue, basically we can grounding via RAG. How this will be handled: when user queries retrieve the context from vector search or whatever by using the LLMs or whatever. On top of that, knowledge base will be used to identify that uh, pulled, pulled, pulled context is the accurate one, accurate, or it's a trustworthy or whatever. Then grounded that to generations. And there should be confident checks needs to be implemented on top of that one, using that knowledge base, whether this specific response a model is providing the information is trustworthy, or that confidence check needs to confirm whether the specific response is accurate or not. So basically, raga pattern builds on top of LLMs. LLMs is like when it's kind of when we are going. So we are running out of time. I will go a bit fast. Okay, a RAG design RAG architecture. What it will do is once like get the context from models. Okay. So a RAG, what it will do is on top of that uh, context, it will apply if there are any processes required or validations are required, if there are any API calls or any services needs to be involved. So those set of sequential tasks or synchronous calls will happen and will identify and will confirm that how the specific request is fulfilled. So we'll go into details. In model drift resilience, monitoring the distribution, track the input features, distributions, and output patterns continuously. Drift shows up as a silent statical shift, not an error. And establishing the baselines, compare the live performance against the frozen validations baseline, not just last week's numbers. We need to build that baseline instead of just some frozen set of baselines. Scheduled retraining. So retrain on a model cascade cadence matches how fast your domain changes, fraud patterns drift faster than product taxonomies. Feedback loops. Capture the real world outcomes. Those are like accepted or overridden decisions and feed them back into evaluation and retrain the data. It means take the feedbacks, how it happens, and return the data again to handle the situations. Yeah, multimodal resilience define in depth. So how we can build multimodal pattern? Primary model, best accuracy, high cost, handles the common cases. So it will primary model will handle most of the scenarios, and it will be accurate, handle the common cases. So when it goes to the next type 2 layer, it's a light older model used if primary times out or fails. If something happened to the primary, this is a fallback mechanism. It will go to this one and it's use the lightweight processes and using the older models to process the request. And rule engines. If fallback mechanism fails, deterministic guardrails for high risk or out of policy cases. These rule engines needs extra human reviews if something goes wrong. It's not that accurate. So human reviews should be required on final reviews. I mean, human reviews required on final actions, escalation tier, low confidence or high stakes decisions. Human in the loop design. Risk collaborated checkpoints. Not every decision needs a human. Route by stakes and confidences, not a blanket review or everything. Explainable surfacing. Show the reviewer why the model decided what it did. Cited sources, confidences, score, key features. Time box reviews. Design the workflow so human no need to spend the time and no need to miss the SLAs. Time box reviews. If reviews are going through, for example, there are some workflows, human reviews are required. If it is going to going to human list, human task queue, then it will wait for a time. Human needs to attend at that specific task needs to be reviewed and processed. So between the time SLS may be missed and escalations will happen. So needs to build time bound boxes to be processed where it's human intention not required. Capture overrides. Every human override is a training signal. Route it back into the feedback loop. Don't let it disappear. If something goes wrong, let it go back to the feedback loop and um, process it again. AI observability. So what we must watch on AI observability: accuracy, drift. Drift is like input output distribution shift, latency, cost, like how the token spend computed per request, hallucination, underground or unavailable answers, instead getting the hallucination wrong answers. Okay, open telemetry and distributed tracing. So Here the structure is like API gateway, retrieval services, LLM interfaces, and post processing. So tracing should be like each layer. These are the different layers and different systems integrated. When the request is coming through gateway, that request needs to be traced. For example, in this case, how much time it is taking at each layer level needs to be traced and needs to be monitored well. Lessons learned, a real world modernization case study. Maybe if we can skip these ones. The challenges in monolithic AI pipeline, a single underwrite model service was a hard dependency for the downstream business lines. When system is monolithic, it's very hard to uh, keep the dependency, that hard dependency through downstream systems. One slow model call back up the whole pipeline. Like throughout the process, if one of the model is down or something happened in monolithic, entire process will go down and it won't process and lose the transaction as well. Undetected drift. If fraud model accuracy had a silent drop over 9 months, the team, I mean, I captured some of the events, but undetected drifts, uh, it's not visible immediately, but during the audits, that will come out if we are not monitoring the on time. And no end-to-end tracing. A customer complained about incorrect rate disclosure took 3 days to find out the root cause across the different distributed systems. All or nothing human reviews. Compliance reviewed 100% on AI assistant decisions, creating reviews backlogs that delayed customer-facing approval by days. As this is monolithic, this process is end-to-end should be completed 100%. So the solution of the architecture is decoupling into microservices and can build in the small services like underwriting, fraud, using that models independently and deployable independently. And events communication goes through events. If anything goes slow, we don't lose the transaction. The event will be stay in a streaming that can be processed once the designated service is up. And we can maintain the orchestration by using the Saga pattern or different approaches. Unified observability and open talent and tracing plus drift monitoring dashboards and replacing the discontinued log systems. And a risk trained human reviews routed by decisions, stakes, and models confident instead of a blanket 100% reviews. This we can skip this one. Lessons learned when we build the system, design for failure, not just for success. So we need to identify all the failure cases and needs to build the system to overcome that failure scenarios. Monitoring not continuously, not periodically. So in distributed systems, this monitoring should continuously go. It's not like a weekly day, end of the day, something like that. So only to catch the issues, monitoring should be enabled to monitor continuously. Automate recovery when you can. So for example, if any system goes down, we need to build any model, a model is down, we need to build the system automatically heal back. Or if there is any failure, circuit breakers needs to be handled. Okay, if the system is not available, what is the second tire we can hit and we can get the response back. And the Saga components we can trigger automatically. And treat governance as a first class citizen. So that specific data governance is the main thing we need to monitor that thing and do the audit traces and to build from a day one then a later point of time. Agentic AI feature. So autonomous agents planned and executed multiple steps, task across the system with minimal human interaction and cross system actions. Agents call different APIs, different data and trigger the workflows. The blast radius of the errors grows accordingly. New guardrails, permissions, scoping, and action approvals and rollback capabilities become essential. And observability gets harder. Tracing a single agent multi-steps reasoning chain is much bigger challenging than tracing a one model. Like if event is processing in multiple models, the tracing is harder than tracing in a single if process is going on single model. Yeah, features of resilience is resilient AI. Self-healing pipelines needs to be built, adaptive architecture. It means scaling and model routing, retraining triggers based on the live observability signs. Trust and built-in property. Ground line, linear, and explainability move from add-ons default architectural requirement, much like a secure data. Regulation and award by design. Architecture that bake in audit trails and model risk management requirements rather than retrofitting them. Okay. Key takeaways: resilience is architecture not bolted on. AI fails differently than infrastructure fails, like what we discussed. Collaborate human oversight to risk. You can't make resilience what you can see. Agentic AI raises the stacks, not the rule book. The same pattern applies just with a bigger blast radius to plan for. Yeah, that's what presentation about. Any questions, discussions?
I feel this was really an interesting topic. I need to go through in depth with that. A lot of things shared and a lot of takeaways for me too. And one thing I liked, my biggest takeaway is building resilience AI systems is not just about selecting the right model or something. It's about designing the entire ecosystem around the model. From architecture to security and the trust and all those observability governance. So that is really good. Thank you so much, Hemasundar. On behalf of Future World Alliance, we are grateful for you to share your knowledge and wisdom here. The session is recorded and we will be sharing it on our YouTube, and it will be even shared on our LinkedIn and other social media platforms as well. Thank you so much and have a great, wonderful rest of your day.
Thank you, Padma. Thank you so much for
Thank you.
providing this offer. Okay.
Thank you
Thank
so
you.
much.
Bye.